So does a process changes its state? The clear case is when a process has an input-output request and it's done, so it's no longer waiting and it will be running, it will be ready. And if the process has actually created the child to do a certain task, when this child finishes execution, it will again be ready. Or if the process is waiting for a signal, when this signal occurs, this interrupt occurs, the process will be ready. So the clear case is when the process is waiting, there are only three options for this process to be ready again. It's when the thing that it's waiting for finishes. But how about the other states? Terminated is also clear. When it finishes execution, it will be terminated. But how the decision or who actually take the decision from to create a new process and then to give the resources to this new process so it will be ready, and who will allow this ready process into the CPU to be executing, and who decided that this process has finishes its time slice or is waiting for an input output, so it has to be out of the CPU and another one has to be allowed in. These types of decisions are made by system softwares, system programs that we call schedulers or schedulers. Mainly there are two types of schedulers: long-time schedulers and short-time schedulers. The short-term scheduler is the one that takes the decision of which process in the ready queue gets into the CPU. And we call it the short-term scheduler because it actually it's invoked in very short periods of time. That is milliseconds. It has to be a very fast code that takes decisions in milliseconds. While the long-term scheduler is the scheduler that selects the processes that would like to be loaded into the memory from the storage device, from the disk, from the hard disk, and load it into the memory. And this selection process happens with criteria. This criteria has to do with the type of the process and how it executes. Some processes do actually use CPU for long times, while other processes tend to be more input-output oriented. Imagine a statistical code, and a movie player. So SPSS, for example, or SPATA, will be using the CPU for calculations for a long time, while a movie player will actually use the CPU for very short times and will be using the output devices, the input-output devices, most of the time. The long-term scheduler is responsible for using a balanced mixture from CPU-bounded processes and input-output bounded processes for better utilization for system resources. And it actually decides how many processes are allowed to coexist in the memory. And here we say that the long-term process determine the degree of multi-programming. So the long-term scheduler is actually involved in terms of minutes, not seconds. That's why it's a long-term scheduler. Sometimes there will be processes waiting for long times for a signal, for an input-output operation, for a child execution. They will be waiting for a long time in the memory, occupying the memory without without being ready to be executed. And that's a waste of resource. Both resources, memory and CPU. Noticing this, the idea of a third scheduler, a medium-term scheduler, has come along, where this scheduler is responsible of swapping out the processes that has been idle for a while, bringing in processes that are ready to execute from a swap space on the hard disk. Maximizing the utilization of both the memory and the CPU. So it swaps out waiting processes and swaps in partially executed processes. And these processes are kept in a small partition of the hard disk dedicated for this process of swapping in, swapping out. حتى اسمه في لينكس swap. So multitasking or multi-programming is quite easy when we are talking about computers, because computers have extended resources. But mobile devices are different because of the limitation of the memory size, of the CPU power. The first generations of iPhone, iOS did not allow multitasking. Now iOS actually allows multitasking in a constrained manner, where it has only one front ground process and multiple background processes. And it's really the level of multitasking in iOS is rather poor. While Android, from the very beginning, allowed multiple processes to be in the foreground and multiple processes to be in the background, with fewer limits, and it uses this concept of a lightweight process called a service. And a service will run on behalf of the actual process. And the service can still continue running even if the process is suspended. Swapping processes in, swapping processes out, bringing new processes from the hard disk to the main memory, allowing processes to actually run on the CPU, or taking the process out of the CPU. All these tasks are performed by processes. The schedulers are processes by themselves, and they need time to run on the CPU to make these decisions. That means for a single process, for a process to be removed from the CPU or to allowed into the CPU or swapped out of the memory to the hard disk or swapped in from the hard disk to the memory, that needs time on the CPU and شنو هي الكلمة changing the process that is running into this in the CPU actually at this moment means that the process control block of this process has to be saved, and the process control block of the new process has to be loaded, and all this is an overhead that we have mentioned earlier, the context switch time. That is why you have to program your schedulers to minimize the context switch time and maximize the CPU utilization at the same time. And this can be very tricky, as we shall see.